Hello students, welcome to the course Network Theory. In the previous 4 to 5 videos, we understand the mesh analysis in detail, right? So today, we'll begin with the concept of node analysis, same way as we have gone through the mesh analysis, okay? With linearly dependent and independent sources for DC and AC networks, okay? So before we do the problems, so we'll try to understand what is meant by node analysis. Okay, so we'll go through all these. Okay, step by step with respect to node analysis also. Okay, what is meant by node analysis? Okay, so in the node voltage analysis, the first difference here is we will apply Kirchhoff's current law. Okay, so that means node. The mentioning of the node itself here you will understand. Where you had earlier mesh. Mesh means what? One closed circuit. So you have to apply here Kirchhoff's voltage law, right? So whereas now a node means what? It is a junction, right? So if you have two and more, so this is called as a node. So when node is there, so there will be currents entering this node, currents leaving this node. Okay, so that's why. So here suitable law is Kirchhoff's current law. Okay, so Kirchhoff's current law is used in nodal analysis to write the equilibrium equations, right? So previously we have done mesh analysis. Okay, we written three mesh equations using the calculator you have solved, right? Same way to write that equations now using node voltage analysis, you require Kirchhoff's current law. Okay, that is one difference. So a node is defined as a junction of two or more branches. That is what I shown you in figure. If we define one node of the network as a reference node, okay, so what we are doing here is, if you have four nodes in a network, so then we will write one of the node as reference node. It is a ground potential, okay, zero potential, and remaining three nodes we will write the equilibrium equations. We call it as node equations. We will write it, okay, a point of zero potential or ground. Okay, the remaining nodes of the network will have a fixed potential relative to this reference. Okay, with respect to this, it will have the fixed potential. So equation relating to all nodes except for the reference node can be written by applying KCL. Okay, so we have to learn now how to apply node equations. Same way what we have done in mesh analysis. There we have applied Kirchhoff's voltage law. Now we will apply Kirchhoff's current law and we will write the equation for the network. And then using calculator or Cramer's rule, we try to solve the node voltages, or it may be branch currents, anything. Okay, so that is what about node voltage analysis. Okay, hope it is clear. So we'll see with an example. Okay, so just to understand how to write an node equations. Okay, so referring to the circuit with three nodes where the lower node 3 is the reference node. Okay, so this one planar network you have. So you have a voltage source here VA and similarly voltage source here VB, and you have the combination of elements. So here resistors I have taken R1, R2, R3, and in between the two meshes here R4, R5. In the case of mesh analysis, I used to call this as mesh 1, mesh 2, and mesh 3. And I need to write three mesh equations, right? This mesh equation, this equation, this equation. So then we have to find out for three unknowns. But the difference to now is in the node analysis, so where we have junctions, okay? So this is the junction we have here. So which is coming over from this path, okay, and coming over from this path and coming over to this path. So that's why this is referred as node 1. Okay, similarly here you have this branch, and this branch, right? So this I will call it as node 2. Okay, and all these branches which is from 1 and 2 which is there downwards, so it is at the ground potential. So all this, okay, so this is at the ground potential. So normally in a circuit like this we will refer, okay, so some circuit they will write mention like this symbol, that means it is a ground. So some circuits in the same manner they will show you like these lines. Okay, so this is nothing but the ground potential. Okay, so that we call it as the third node, node 3 I have written here. Okay, so doing this, what will happen here is the same network. In the case of mesh analysis we used to do three equations. Now we are writing only two equations, that is for node 1 and node 2. Okay, and we are not writing equation for node 3. Okay, so by doing this way we are reducing one equation. Okay, so we are able to solve v1 and v2. From that v1 v2 and the remaining va vb, so we are able to find the currents, mesh currents also we can able to find. Okay, as we have seen in mesh analysis, we used to find out the voltage across certain resistance. That means what? A branch voltage we are calculating. Okay, so that is branch voltage is nothing but this junction voltage itself. Okay, how we are calculating that? First we used to calculate the mesh currents, and then we used to use Ohm's law, right? That resistance with I2 minus I3 current we used to do, right? From that we used to find out the voltage. Same way, now we find out the node voltages, and from that we can find out these mesh currents also. Okay, so what is the advantage here is writing number of equation is only 2. So in the calculator also you have to use number of unknowns 2. Okay, so in this network, okay, so for an example of a 3 mesh network, you require only 2 node equations. Okay, so that is what the difference you will see, and that's why mesh analysis will be less used in the network analysis. Okay, network whatever you are studying this, so you have two methods. So normally they will go for node voltage analysis. That's why this part is very important. Okay, so mesh analysis we have told you, problem wise it is also important, but in the real time, so real time circuit analysis, so they will more prefer node analysis compared to mesh analysis. Okay, and there is also some consequences there. So when you have to find a branch current, no, we can straight away go for mesh analysis, because finding node voltage and then going for branch current, it is a reverse process, right? Same way, when you have to calculate the junction voltages, okay, then no need to go for mesh analysis and then calculate voltage. It is again a big process. So instead straight away we can use the node analysis. So like that, so depends on you. So which you have parameters you have to calculate from the network. Based on that you will use either of these methods. Okay, so we can arbitrarily choose any node as the reference node. Okay, so however it is a convenient to choose the node with most connected branches as the reference node. Okay, so this is you have to remember. So reference node, why I have taken 3 only? Because all these branches are connected to this. One is also connected here. See, one branch, most of the branches, one is connected here, this branch is also connected, then this branch is connected, and this branch is connected. So majority of the branch is connected to this one. That's why this is kept at ground potential. Okay, so hence node 3 is chosen as the reference node in this example. Okay, hope it is clear. Okay, so as we solve the problem, so you'll understand how exactly it will come equations. Okay, so there are 3 nodes here, hence number of equations based on KCL will be total number of nodes minus 1, because in the present context we will have only 2 KCL equations referred to as node equations. One is reference, no, we are not writing equations for that. Okay, so for applying KCL at node 1 and node 2, we assume that all the currents leave these nodes as shown in figure. Okay, so because it is not a problem here, just an example, we need to assume right here current direction. So we'll consider here all the currents are leaving the node. Okay, from 1 it is leaving. Okay, so that is what the assumption we'll make and apply like that. So they are leaving. They are leaving. Okay, so they are leaving the junction. Okay, so similarly here they are leaving. Okay, so when we are considering same way, like that. Okay, so these are assumptions we'll make, and we'll try to write the equations now. Okay, even the general equations also there, that also will show you next. So this with respect to first one, the same network I have written like this. So instead of writing VA connected to 3 here, I have written as VA here, and this with respect to 1, the voltage is V1. Okay, as we have with respect to mesh 1, mesh current is I1, have how we have taken. Same way we'll consider node as V1. Okay, so then remaining resistors whatever connected, R1, R2 and R4 are connected, and with respect to that resistors we have given name. Okay, with respect to R1 I have called I1, with respect to R2 I have called I2, with respect to R4 I have called I4. That is nothing but the branch currents. Okay, so these are the branch currents. So now we have to apply the KCL here. So for this network, if you apply KCL, what you will get? So I1 plus I2 plus I4 is equal to 0, because all the currents are leaving the node. Okay, so no need to equate here. So if some current is entering the node, then we would have told I2 plus I4 is equal to I1. Okay, so all are leaving, so all the 3 summation is equal to 0. Okay, so now we need to use the Ohm's law next. What is I1 current here? I1 current means here it is V1 voltage minus VA voltage. So VA is also voltage is there. So V1 minus VA by R1, that is I1 current. Ohm's law, V by R, right? So V is not only 1 here. So whereas in the case of this branch here now, I2, oh sorry, this branch, So this side you have V2 and here you have V1. So that's why it is V1 minus V2 by R2. Whereas in this branch, so you have V3 now. So this is 3 means it is V3. But what is the value of V3? It is 0. Okay. So that's why here V1 minus V3 by R4. Resistance is R4 here is equal to 0. Since V3 is 0, I have mentioned here as 0. Okay. So now if you simplify this, if you group all the V1 by V1 terms, okay, so here V1 term is there, here V1 term is there, here V1 term is there. So if you group that V1 terms, so you will have 1 by R1 plus 1 by R2 plus 1 by R4. And you have only one V2 term here minus V2 by R2. So that is written over here. Okay. And the right side, what you have? Constant term. That is this voltage minus VA by R1 is there. So if you take right side, it will become plus VA by R1. Okay. So this is a type of a conductances. The reciprocal of resistances is nothing but one conductances. In the case of mesh currents, what you had? Resistances R1 plus R2 plus R4 into I1 like that, right? R2 into I2 like that you had. But now it is voltage. So V by R fashion it will come equation. That's why you will have 1 by R1 plus 1 by R2 plus 1 by R4. Okay. So if you analyze this with self, the general equation. So the self node, so all the resistances connected to this node 1 are self, that will be plus. Okay, see here R1 R2 R4, that is what here plus is there, R1 R2 R4, and here plus you have, and which is mutual between this node and this node, which is mutual here, R2 is mutual, right? So that's why here minus sign is there, and you have V2 by R2. Okay, so that resistor it will be there in reciprocal. Okay, and what is the current here coming to this node? That is VA was there, right? So if the beginning circuit, if you have seen, so you had plus minus. So if you convert this voltage source in series with resistance into a current source, what will happen? VA by R1. Okay, so that is what written over here. It is the current. Instead of writing this as some current, we have written as in terms of voltage by resistance. Okay, so this is about the first node equation. Similarly, we can write the second node equation. So both I am showing you generalized equation and the applying KCL. Okay, so first you write the KCL because that is familiar with the, and as you practiced, so then you can write the general equations straight away. Okay. Similarly, second node. So second node, if you see the network there, what you have? R2 at the V1 side, R3 at the VB side. So you have one more voltage here VB, and then you have the R5. Okay. So with respect to that resistance, I have called here with R2 I2 current, here I3 current, and here I5 current. Okay. Again, 3 is the common node here, which is V3. Value of that will be 0. Okay. Ground potential. Okay. Here also you have to write equation. So now V2 is the self node, and between V2 and V1 you have the R2. But if you apply the KCL here again, so it is all the currents are leaving the node. That is the assumption we have taken, right? I2 plus I3 plus I5 is equal to 0. Okay. Then what is I2 current in this case now? I2 is, so which direction? So arrow is this side, right? So that means what? So V2 minus V1 by R2. Okay. So that is the I2 current. And I3, where is I3? V2 minus VB. So VB is there. So V2 minus VB by R3. And where is R5? This one I5. V2 minus V3. So again here V2 minus V3 by R5. So V3 is 0. That's why here mentioned 0. So same way now you simplify. So you have only one V1 term. Okay. So minus V1 by R2. That is written over here. And there are three V2 terms. Here V2 terms. V2 terms. Okay. So if you group that, so what you will get? 1 by R2 plus 1 by R3 plus 1 by R5 into V2. V2 is common. Okay. And if you take the constant voltage outside, so minus VB by R3, take it right side, you'll have plus VB by R3. Again here it can come minus based on the notation here. So here it is having plus minus. Okay. So that's why it is plus VB. In case if it is minus plus, you would have minus VB. And while writing equation, you will write V2 minus minus VB. That means V2 plus VB will come, and that plus VB if you take right side minus VB. Okay. So as we solve the problem, so these things will be clear to you. Okay. So this is how we write the node equations. Okay. The same network, what you have written 3 equations in mesh analysis, now we have reduced to only 2 equations. Okay. So now This is a general example. Same way, if the network is given, if you write the equation, so use the calculator and you solve the node voltages V1 and V2. So from, if you know V1, V2, then easily you can calculate this branch current. This is nothing but branch current, I2, I3, I5. What is I2? V2 minus V1 by R2. So that means V2 and V1 should be known, right? Same way. So here also V2 minus VB by R3, that is I3 current, means VB is already known. That is a constant, right? Given it maybe in the network. V2 is not known. That is we have to calculate, right? So from the node voltages, we are able to find the branch currents also. Okay. So this is the idea of the node voltage analysis. Okay. So now this same equation, if you write it in matrix form for your Cramer's rule, okay, if you write the determinant and delta 1, same way if you solve, okay, you can get the V1, V2. So normally for the DC network, calculator is sufficient, whereas in the case of AC network, as we have seen in previous video, you require the Cramer's rule, right? So that's why matrix form, how we'll write? We'll write the coefficient of V1 and V2 in the matrix form. So since it is only two equations now, so 2 by 2 matrix, 1 by R1 plus 1 by R2 plus R4, and here you have minus 1 by R2. Same way here also you have minus 1 by R2, and here R2 R3 plus 1 by R2 plus 1 by R3 plus 1 by R5. Instead of current in previous case, now you have voltages. That's why node voltage. That is mesh current analysis. This is node voltage analysis. Okay. So earlier you had here voltages in the previous mesh analysis. Now you have currents in terms of V by R. Okay, VA by R1, VB by R3, nothing but it is current itself. Okay, the above matrix equation can be solved for node voltages V1 and V2 using Cramer's rule, okay, of determinant. So once V1 and V2 are obtained, what you can do further, okay, that also will show with example. Using Ohm's law, we can find all the branch currents as I shown you earlier, I2, I3, I5, okay, and hence the solution of the network is obtained. Okay, by this, this is what network analysis means. Okay, so hope you have understood after learning mesh analysis and now this node analysis. So what you are going to do? So now if you have a circuitry in your home, right? So maybe a TV circuit, or it may be a mobile circuit, or it may be a refrigerator circuit, anything. So if it is in the, so how it will be in the form of a circuit. So that circuit will be connected with elements, resistor, inductor, capacitor combination. Okay, so you need to able to analyze if any fault is there. You need to able to analyze, right? So here to here how much voltage is there, here to here how much current is there. So all these small analysis will be carried out, okay, using these basic laws. Okay, mesh analysis and node voltage analysis, the very foundation for this network theory course. Okay, even if you go for next theorems, okay, initial voltages or the two-port networks, we will be learning in the coming modules. For that, the basic is this node voltage analysis or mesh analysis. Okay, so that is what we will be doing here. Okay, so in the mesh currents, so we'll be writing mesh equations and solving the mesh currents, and then using Ohm's law we are finding the voltages across the node. Okay, so in the node analysis we are finding the node voltages using the KCL, and then using the Ohm's law we are able to find each of the branch currents. Okay, so because voltage is there, so just you divide it by the certain branch resistance, so you'll get the branch currents. Okay, so that is what about this. Okay, node voltage analysis. So the generalized node equation can also be written as we have shown in the case of mesh analysis. So here in the mesh analysis, how we have written, it is matrix of Z into I equal to E. We have written this again Ohm's law. E means V is equal to IR, but it is a complex notation. Z means R plus JX. So now its reciprocal of impedance is Y. Okay, that is admittance we say, and then I is here becomes E in the case of node voltage analysis. Okay, equal to I, this is equal to I. So meaning what? So I is equal to, in the case of DC network we are writing V by R. So what is 1 by R? Reciprocal of resistance is also called as conductance. Okay, conductance G into V. I is equal to G into V. Same way in the case of DC AC network, this I is equal to E by Z or E into admittance. Okay, so that is what written over here. The same fashion my equations are written. So all the self node, so y11 e1, y12 e2, y13 e3, for 3 node equations it is written here equal to i1. Similarly y21 e1, y22 e2, y23 e3 equal to i2, y31 e1, y32 e2, y33 e3 equal to i3. So meaning what here? So all the self, that is y11 with respect to node 1, y22 means self node of node 2, y33, all these three will have positive coefficient here. Okay, and the remaining, the mutual y12 y21 y13 y31 y23 y32, all these are minus. Okay, so they will be mutual admittances, okay, or mutual conductances we say. Okay, and this is the current we will have. Okay, so this is about the concept of node voltage analysis. I hope you have understood some percentage, not completely. So in the next video we'll solve the problems on node voltage analysis. So then you will be getting clarified more on this. Okay, so with this we'll end this session here. Okay, in the next video we'll solve the problems. Okay, so thank you.